Good morning. How are you all doing today? Well, that doesn't sound much of a resounding enthusiasm here. How are you all doing today? Aren't you enjoying the weather here? Let me tell you, as a Korean, you came to this country at the best possible time. It's the most beautiful part of the year. And so, of course, you should stay in the conference, attend every session as possible. But if you get a bit bored, it's okay to sneak out a little bit and enjoy the weather. I didn't say that. I don't think the general chair recognizes what I just said. But anyway, my name is David Han. My role for the day is to introduce our distinguished keynote speaker. So she is quite accomplished, and therefore I have to keep a list, right? If you don't mind. Oops. I'm in business now. I really have to confess, this is one of the most privileged and honored opportunity for me to introduce today's keynote speaker. Yejin Choi is Brett Helsel Professor at the Paul G. Allen School of Computer Science and Engineering at the University of Washington, and a Senior Research Manager at AI2, overseeing the project Mosaic. Her research interest covers in a wide range of problems, including common sense knowledge and reasoning, neurosymbolic integration, multimodal representation learning, and AI for social good. For those who pursued for these prestigious prizes in the areas of AI recently, she pretty much had beaten most of the competitions for the last 3 years or so, including these prizes: Outstanding Paper Award at ICML 2022, Best Paper Award at NAACL 2022, more notably, being a co-recipient of the ACL Test of Time Award in 2021, equally, CBPR Longet-Higgins Prize in 2021, NeurIPS Outstanding Paper Award in 2021, Triple AI Outstanding Paper Award in 2020, Borg Early Career Award in 2018, Inaugural Alexa Prize Challenge in 2017, ICCB MAR Prize in 2013, but more telling is this: in 2016, IEEE AI picked her one of the top 10 to watch. This was back in 2016. Their prediction was right on target. And for those, if you are so eager in winning some of these prestigious prizes in the next few years, I'm sorry, but you are against a very stiff competition. Without any further ado, Professor Yejin Choi.
Okay, I'm very excited to be here. Thank you so much for joining me in a very early morning. So this talk is going to be about David and Goliath, the art of leaderboarding in the era of extreme scale neural models. So why should we worry about this is because people do ask me questions like, well, are you sure we can't reach AGI just by scaling things up? GPT-3 seems so magical. And I actually get questions like this from a journalist, whether we may just solve AGI by scaling things up. And then there are concerns by students whether it's even possible to do anything impactful from academia without having that sort of a compute available. So in this talk, I would like to discuss our path toward doing something impactful, even without compute. And it's good to draw inspirations from old wisdom, The Art of War. In that book, basically the idea is that know your enemy, choose your battles, innovate your weapons. Now we need to reinterpret that for the modern deep learning era, where knowing your enemy means you need better evaluation strategies that has realism and scrutiny by considering adversarial and out-of-domain distribution. And then also choosing your battles could mean that you think about new tasks that deep neural models may not be able to handle quite well beyond the existing leaderboards. And finally, innovate your weapons. These are about new algorithms and new data sets. So in this talk, I'm going to talk about 3 different pieces of work that share a recurring theme of smaller models can be better, and knowledge is power. Okay, let me start with the second one. So I switched the order last night. So Neurologic A*ESC just won a Best Paper Award at NACL this year, which actually builds on our previous work, Neurologic Decoding. In this talk, I'm going to just combine the two and tell you, just merge the story, because one thing builds on the other. So the idea is that we hear how larger models do better, but the truth is search algorithms can lift quite a bit. So for example, Monte Carlo tree search was one of the key ingredients of AlphaGo, without which AlphaGo could have not happened. So classical AI was a lot about search algorithms, and that's how I started studying computer science even at the beginning. So in this talk, we're going to draw from this classical search algorithms and see whether we can do much better job at solving some of the harder challenges for neural language models. So when you use language models, there typically is this decoding algorithm sitting on top of language models that are not as it's usually decoding algorithm is there, and people may not talk about it very much, but that is actually what could be important. And in particular, in this talk, I'm going to talk about how we can integrate logic constraints provided in conjunctive normal forms flexibly during this decoding algorithm without having to retrain the whole thing end to end. And by doing so, we might be able to do a variety of different tasks, such as, sorry, I should rerun the whole sequence. So if we have a decoding algorithm, we can use that as a plug and play on top of neural language models in order to solve a variety of different tasks, such as text, table-to-text generation or image captioning, or machine translation. Okay, so neurologic decoding in a nutshell is a search algorithm that requires drinking lots of coffee and then implementing the search algorithm correctly, which we are not going to go into the detail right now because it's too early in the morning. I don't know if you had enough of coffee. So I just shrink it down to saying that it's a logic-guided search algorithm that requires a bit of care because when we think about clauses in the conjunctive normal forms, they are either satisfied and unsatisfied in a way that's either irreversible or reversible. And these state changes are dynamic, so we need to carefully keep track of this during search. Just leave it at that. So that's neurologic decoding so far. And imagine a task in which you need to write a sentence that includes these following 3 words: car and drive and snow. And so far, let's assume that we generated already. I drive my car, and then I need to deal with the snow. With that in mind, probably it's better to choose winter than summer, but the previous neurologic decoding algorithm will still prefer summer in this case because the search the search history only concerns either the past or the present time, so it cannot really project into the future. So ideally, what we want to do is to be able to project into the future. That's what A-star search was all about. It's, I don't know, within the first few chapters of AI textbook. So we draw from that idea, but here it's just A-star-esque search, not A-star search, because when you deal with neural language models, it's not possible to design an admissible heuristics. So it's heuristic algorithms, classical search algorithm, but not admissible. So there are different ways to project into the future, and one way to do so might be based on greedy look ahead. So the details are not very important, but I will just provide you with some high-level intuition about how we might design the future projection heuristics. So one way to do that is greedy look ahead. Another way to do that, perhaps a better way to do that, is beam look ahead. So we do a bit of beam search toward the future and then think about what's a better choice. Or we can also do sampling-based look ahead in order to encourage diversity in the search path toward the future. So anyhow, when we look at the outcome of neurologic decoding for this common gen task, which is given some keywords, you need to generate some sentence that includes all the keywords, we find that the empirical results are surprising in that unsupervised methods can do better than supervised methods. So let me unpack this a little bit. Looks like I cannot really have this doesn't work, does it? Okay, so coverage, if we just look at coverage, that's a percentage of the time that constraints are satisfied, so the higher is better, and ideally it should be 100% of constraint satisfaction. The blue line is a supervised model, so that's what everyone else does. Supervised model, seq-to-seq training over lots of data points, and then on the x-axis you see the model size increasing. So the larger model does do better, but it's never 100%. Whereas neurologic decoding, so green and yellow lines correspond to neurologic decoding used on top of either supervised model or unsupervised model. What I mean by unsupervised model is pre-trained language models off the shelf without fine-tuning at all. It's a zero shot. So you will see that regardless whether you use neurologic decoding on top of supervised or unsupervised, they work similarly. And then it's not just doing constraint satisfaction at the cost of quality of generation either. So if you look at Roger score and Meteor score, which in this case correlates well with the quality of the text, here again higher is better. We see that, again, neurologic decoding just outperforms the supervised approaches. What's even more exciting is that unsupervised neurologic on top of a smaller model already outperforms the larger models that are supervised. And we don't hear this type of result very often. So that's very surprising to us that decoding algorithm can lift the performance of fine-tuned neural models quite a bit. So in the paper, we report a lot more different types of tasks other than the common gen that we just looked at. But across the board, neurologic decoding can boost the performance of neural language models quite a bit, even after fine-tuning or unsupervised. Okay, so that's one way to beat leaderboards by having smaller model but having more powerful algorithms. So let me now move to the next segment, the symbolic knowledge distillation, which, by the way, is going to build on neurologic decoding eventually. But for now, let me just highlight that there's this YouTube channel that highlighted our paper right after we archived it. And last time I checked, the view count was about 20,000. And I don't know what the channel does to get that kind of view counts. I never get this kind of view counts for my own talks. But anyway, so the idea behind this work is that, well, despite human level or even superhuman level performances on leaderboards, the state-of-the-art models are brittle when provided with adversarial or out-of-domain examples. So it's almost as if deep learning knows how to solve a data set without solving the underlying task properly. So we want to somehow close this gap between how humans learn about the world versus how neural models just learn the surface patterns of the data. And one missing but important ingredient is the common sense knowledge. So here I'm going to define it as the basic level of practical knowledge and reasoning concerning everyday situations and events that are commonly shared among most people. I didn't say all of us, but it's just most of people. So here's one example. It's okay to keep the closet door open, but it's not okay to keep fridge door open because the food inside might go bad. Importantly, this type of inference is always diffeasible with additional context. So for example, if the refrigerator is not even plugged into the wall, who cares? So these are usually just general rules of thumbs that are generally true, but not necessarily. And these are, in fact, how we interact with each other and live in a safe way. And so as AI becomes more and more integrated with human lives, it's important for them to understand the rules that we go by our daily lives. So the underlying idea behind this work is that language models are not immediately knowledge models, and we need to think about common sense knowledge models as the first-class citizen of our research goals. So with that in mind, we worked on symbolic common sense knowledge graph called Atomic, as well as Comet, neural common sense models that are trained on top of this atomic knowledge graph. And I will give you a bit of context behind it before we reach to the symbolic knowledge distillation. But these are basically the background work that we build on. And our initial work, Atomic, was fully crowdsourced as of 2020, when we had this new updated version of Comet Atomic 2020. Still, the Atomic part was fully crowdsourced. Why do I highlight that? Is because I'm going to now lift that limitation. But for now, let me give you an example of what Atomic 2020 looks like. So given center event like X gets X's car repaired, so maybe Sarah gets her car repaired, you can immediately think about a variety of things that may be true in that particular context. So for example, you probably need some money and mechanics in order to get your car repaired, and as a result, you may need to call Uber or Kakao Taxi to get back home. So that's Atomic. And then Atomic 2020 had additional common sense relations, such as maybe money can be used for paying bills, but also if you really want it, you can fold it into origami if it's a paper bill. And so these are about the stereotypical use cases of objects, as well as what are affordable in that objects, even if it's not stereotypical use cases. And this resource also has other fun common sense inferences, such as can be hindered by, which means counterfactual context in which the event cannot happen. Oops, sorry, I did it again. So for example, you cannot really get your car repaired if you completely damage the car, total the car, then you cannot get it repaired. So there are other many different inference types annotated in this corpus. It's fairly big. How big? It's more than 1.3 million if-then rules over 23 different relation types or inference types. Again, fully crowdsourced as of 2 years ago. All right, so what benefit does this kind of symbolic graph provide is that so if you train a model like a Comet on top of that symbolic knowledge graph and then compare with the GPT-3, which is so large, it doesn't even fit into the slide. And it's more than 400 times bigger than our small Comet. Then we can compare the performance. So here, the performance is accuracy judged by humans. And the task is that given a single node and inference type, you have to reason about what may be true. And you have to generate the output, so it's a hard task. And I was really surprised by how GPT-3 is suddenly at 73% accuracy. This, we are going to come back to it in a bit. Compared to GPT-2, which was so bad before. And just by scaling things up, suddenly GPT-3 knows a lot about common sense reasoning. But you know, most of us cannot really fit GPT-3 anywhere, let alone slide. You know, even if you have computers, usually you cannot really fit that. So it's nice to have a smaller model like Comet that's so much easier to work with, and then it also works better. It's a considerable gap in terms of accuracy. But this got us thinking that, wait a minute, there's something really amazing going on with GPT-3, which I'm going to come back to it. But let me just share a bit of creative work that other people have done, building on top of Comet and Atomic. So people all over the world came up with lots of creative ideas to enable research toward conversations and figurative language understanding and storytelling and even fantasy game environments. So seeing how people do creative work out of these resources, we wanted to improve it. But now the question is how? So here comes the symbolic knowledge distillation finally. From neural language models to causal common sense models, the idea is that this guy, GPT-3, is so big, and it's kind of good, but not good enough. So what we're going to do is we're going to do symbolic knowledge distillation to make it smaller, but better. Now, wait a minute. You don't normally make things better by making it smaller. So how is that even possible, you might wonder. So we're going to draw from knowledge distillation that I'm going to talk about in a bit. But the reason why this can be possible is because this filter that we're using has this long funnel that includes critic in the middle. So, and then as a byproduct, it's going to generate a symbolic knowledge graph in the middle. So building on Hinton's knowledge distillation idea, which was to compress teacher model down to student model by optimizing the cross entropy between the two models, we're going to build on this, but the original idea was developed for classification task, and here we cannot really enumerate over all possible output space. Why? Because there are exponentially many. But that's okay, because everyone else does just sampling and approximation by sampling, so we can do that here as well. No problem. It turns out if we do the sampling, the byproduct of doing that is the symbolic knowledge graph, because we can reinterpret the samples as a symbolic graph. In doing so, when we do this, by the way, we can compare how human-authored Atomic, the original Atomic, compares to the machine-authored, in this case GPT-3-authored knowledge graph. And one way to compare that is by comparing the size. So here, y-axis shows the size of the symbolic knowledge graph in millions. And here, the Atomic 2020 portion is not as big as 1.3 million that I told you earlier, because we're looking at a subset of the inference types only with respect to 7 different inference types in this study that are to do with the causal common sense inferences. So we only have less than 1 million when we crowdsourced Atomic 2020. Compared to that, when we ask GPT-3 to write Atomic, it's much bigger. But here, the green portion is good portion, and black portion is bad portion. So as you can see, GPT-3 is about 73% good, which means about 30% is bad, black. Now, what we do is a very simple idea. We train a critic model based on Roberta that's small, and then supervised on medium-sized annotated data about which knowledge is good, which knowledge is bad. By the way, this critic cannot be very good. It's a very poor vanilla model that doesn't really have a common sense knowledge, so its prediction quality is not very good. But if we're willing to throw away a lot, then it's good enough to throw away most of the black portion. It also throws away a lot of the green portion. But the end result is such that it's still much bigger than how much we were able to crowdsource by humans. So the final Atomic 10x data set is still much larger than what humans were able to crowdsource, and then it's actually better quality compared to what human did. Then we might wonder, well, but is it actually good if you train the common sense model, the neural models on top of that resulting symbolic knowledge graph? So here, as a reminder, the GPT-3. So if you just use GPT-3, was about 73%. Now, it turns out if you train the GPT-2 model on top of that sample of knowledge that we generated, on its own, the student is already better than the teacher model without doing anything. So that's an interesting phenomenon that we haven't seen before, but that is what happens. It's not as good as GPT-2 trained on human-authored Atomic, but the final product that's based on critic model combined with the GPT-3 leads to the best COMET model that we have attained so far. So this is a very exciting result in my mind because it gives us new ways to build the symbolic knowledge graph. And it's actually also for the first time that AI-authored knowledge graph is actually better than humans by all criteria: accuracy, scale, value, and diversity. Even diversity, the neural models are not repeating itself. It's actually providing diverse and creative common sense annotations. So this was quite exciting for us, but I didn't like the fact that we had to rely on GPT-3 in this work. So then we wanted to see whether we can get rid of GPT-3 part. So this is new work that's not even on archive yet. We're going to archive it soon, where we're going to focus on slightly different problem of generic induction. So it's what I mean by generic is generic statement such as birds can fly. So we no longer have this if-then rule statements. It's just what is generally factually true, stated in a simple sentence such as this: birds can fly. Now the question is, can we get rid of GPT-3? GPT-2 looked really bad, though, as you saw earlier. So here, the reason why it might work is because of neurologic decoding that we saw earlier. So what we are going to do is, given a concept like a bicycle, if you try to use GPT-2 off the shelf and let it generate something about bicycle, you get completely random sentences that are no good for the purpose of common sense knowledge generation. But you can use neurologic decoding to guide the style of a sentence such that, keep it simple, just use past, don't use a past or future tense, don't use storytelling pronouns and stuff like that, then you get clean, nice sentences such as bicycles are pedals, which are in the correct form, but not correct in terms of the content. So neurologic decoding can provide a very powerful way to control the style of language without being able to control the actual correctness of that content. So it turns out after neurologic decoding, about 40% of the generated sentences are actually good. So 40% from almost 0% is a huge jump, but it's still not good enough, but that's no problem because we can use this filtering idea again by training a critic model. And if that's not enough, then optionally, we can also run off-the-shelf natural language inference models in order to detect all the contradictions within the generated pairs, and then formulate max set solver to throw away contradicting ones to filter down the quality even more. So then what happens in the end? So compared to GPT-3. So it turns out GPT-3 is really shockingly good in this task. So this is a precision recall curve, and the red line is GPT-3, which is almost at 80% zone for a while in terms of precision, and then it tails off. So that's really difficult baseline to beat, especially if you're trying to beat that with GPT-2, which is pretty much no good. But this result shows that, well, the green line, our method, can do better than GPT-3. And that's because of the power of algorithms. I really think that we can do a lot more with algorithms, but we may be overlooking the power of algorithms because everybody is talking about how scale matters. In fact, the scale has something to do with information complexity and quantity, and I think algorithm can lift that quite a bit as well. Okay, so in sum, the resulting resource compared to the generic KB, that's prior resource of this sort that was based on automatic extraction of generic statement from the web. So that's more like information extraction style approach. So the previous resource was much smaller compared to the final result we have here. And again, as you see, when we start off from GPT-2, the quality was really bad. It was only 40% good. Even after neurologic decoding, it's 40% good. If you don't use a neurologic decoding, it's about 0 to 1% good. Not even 1%, it's closer to 0%. So decoding algorithm can really unleash the hidden potentials of neural language models quite a bit. And then if you add the critic model and other learning or inference algorithms on top, then you can improve the performance further up by over-generating and then filtering out a lot. So again, small models can do better. Actually, I'm going to skip that part. Finally, I'm going to move to the last part, which is common sense morality. So this is about Delphi. How many of you have heard about Delphi? Okay. Some of you, but not all. Okay, so this is about addressing the challenge of machine ethics. And well, neural language models are almost being deployed, if not deployed already in different contexts. So here's a demo that you can check out if you like, delphi.allandai.org. And since many of you don't seem to know about it, let me just tell you what the demo is capable of. So if you give an example like killing a bear, Delphi says it's wrong. By the way, it has never seen training example like this before. How about killing a bear to save your child? Then it's okay. Maybe saving your child sounds positive, so how about to please your child? Then it says it's wrong. So then maybe it's really about saving your child. So how about explode the nuclear bomb in order to save your child? And then it says it's wrong. So you can do free-form QA like this. In our original version, we supported relative QA, which we took down. But it was able to compare pairwise sentences such as stabbing someone with a cheeseburger versus stabbing someone over a cheeseburger. This requires very complex reasoning because, first of all, if you say stabbing someone with a cheeseburger, cheeseburger is too soft to stab someone with. It's such a rude thing to do, but you're not going to injure anybody compared to stabbing someone over a cheeseburger. That implies that you're using a knife as the tool. Just linguistic convention is such that if you don't mention, you're using the obvious choice. So it requires complex reasoning. And then finally, you can also ask yes or no questions like, is it okay to fire someone because they're gay? Then it says it's not okay. Okay, so it turns out Delphi is robust against computational situations. So for example, mowing the lawn, out of context is expected. How about late at night? That's not okay. But that's okay if you live in the middle of nowhere. Ignoring a phone call. That's rude, but if it's a non-phone call, then it's okay. But from my friend, that's rude. But what if I just had a fight with a friend? Then it's okay. How about during my working hours? That's okay to ignore. Outside my working hours, that's rude. But what if it's my boss's call during my working hours? That's wrong. But what if I'm in the middle of a meeting? Even if it's my boss's call, then it's okay to ignore. So you can see how things get really complex even with this short text span. Our moral judgments are highly contextual. There's never really one rule that works for everyone at every situation. The challenge is that it's a highly flexible system that you and I, us humans, share. And for some reason, we somehow figure out when it's okay, when it's not okay. Even if you've never seen examples like this before, you can still reason on the fly. So here's another example that Delphi happens to know a little bit. It knows a bit of a common sense as well for reasons I will share with you in a bit. Drinking milk, if I'm lactose tolerant, probably not okay. But soy milk, it's okay. So within our training and test split of our data set that I will describe in a bit, the Delphi performance is much better than GPT-3, either 0 shot, few shot, 3 shot, 30 shot. Importantly, 0 shot performance is barely better than chance. That's not good, which means off-the-shelf neural language models, unless we do something about it, didn't really acquire human moral or ethical reasoning capabilities. It's good that it can do much better very fast with more examples, but still, like I said earlier, GPT-3 is too large for people's, a lot of people's use cases, so it's just still good to develop something smaller, and then we can also make it better. So you might wonder, how did we do this? So the power in this case really comes from data. So far we saw power coming from algorithms or different types of learning techniques. Here the power really comes from data. In particular, we have this common sense norm bank that encodes 1.7 million people's ethical judgments on everyday situations. And this combines cultural norms, social norms, and ethical norms, because these things don't have clean-cut boundaries. They're all mixed in. In particular, the corpus is drawn from 5 already existing data sets that are not designed to be used for QA, but we automatically converted them into QA form. As you may notice, the 5 data sets are all from recent years, 2020 or 2021. And actually 4 out of these 5 are from our own lab, and what does matter is mostly these 2. Especially the first one is what gives the most power to Delphi, and then social bias frames is what trains Delphi against racism and sexism, without which the language models are really riddled with bad stuff, so we see a problem right away. So let me tell you a little bit about social chemistry 101. This is our previous work presented at EMNOP. And the motivation behind this is that if you ask GPT-3 whether running a blender at 5 a.m. is rude or not, because ... let it finish. It says, well, you can wake up the entire neighborhood. What kind of blender is that? You can only do it if you are making a thick smoothie, and also need to incorporate some ice though. So it says something very funny, cute, haha, maybe no harm made. But what if you ask questions like, it's okay to post the fake news if ... It says, yeah, it's okay if it's interest of the people, whatever that means. Try again, because GPT-3 always samples. So there's a bit of randomness, and it says like, yeah, it's okay if you support your favorite political party's agenda. So even if it hurts the country, by the way. So why does GPT-3 say this? Is it because that's what people did say out loud on the internet. So the internet data in the wild is riddled with a lot of problematic content. And just by scaling things up, GPT-3 is not going to learn what is right from wrong. We really have to teach it differently. And if we really think about how we teach our children, we have to tell them what's right from wrong. It's not the case that they can just go and read online resources and figure that out themselves. Probably it's not going to be very good result if you just let them be. So similarly, we do need to tame AI by teaching it explicitly. It turns out teaching it explicitly is not easy because human lives, the rules that we go by is complicated. So here's an example to consider. Asking my boyfriend to stop being friends with his ex. So in a situation like this, depending on whom you ask and what they care, you get all sorts of different judgments, which is why there are also TV shows, soap dramas that people watch and people argue who's right, who's wrong, because it's not that clean cut. In many situations in human lives, the right and wrong can be ambiguous, depending on what do you care more about. So if you care more about loyalty and betrayal versus care and harm, you're going to have a different rule of thumb so that you're going to apply to that particular situation. So for any given situation paired with rule of thumb or ROT, in this corpus, we provide 12 different structured annotations or semi-structured annotations. And some of these annotations are derived from the moral foundation theory by Jonathan Haidt. And I'm not going to go into the details of the annotations, but I'll just mention that the annotation is very rich. It includes 300,000 of rules of thumbs that people provided on hundreds of thousands of real-life situations. Importantly, the real-life situations are collected from online sources like Reddit, because people discuss a lot of morally thorny situations there. But the rules of thumbs and then the 12 structured annotations are done by carefully selected crowd workers. Okay, so that's the social chemistry. And then what we do is we trained Unicorn, that's our own common sense QA model that is in return trained on the Google's T511B. This is just pre-trained, one of the many pre-trained language models. And then Delphi comes out of it. So you might wonder why it's built on top of common sense QA though, because moral reasoning has nothing to do with common sense reasoning. Well, you cannot really divide the two, because as we saw earlier in this example, in order to make this distinction, you do need to know something about common sense reasoning as well. Yeah, and also like the trolley examples require more of that too. And so moral reasoning, if we really want to support it, requires language understanding, common sense understanding, as well as morals and norms. It's a huge challenge. And here's another example supporting this position. So you may have heard about this Alexa suggesting 10-year-old child to touch a coin, metal coin, to an exposed plug socket. That's such a wrong advice to make. And the reason why Alexa did it is because apparently this is a thing on the internet. People talk about it a lot as a daring thing to do, but it's not something that you should recommend to a human being. So DeFi does know that this is dangerous. And again, the fact that this is unsafe requires understanding about basic common sense knowledge that it's a dangerous thing to do. So again, the demo is at delphi.lnai.org if you want to try that out. Okay, so never did I imagine, by the way, when we archived this, we got the kind of attention we did end up getting. We had to take down the relative comparison mode immediately because that was the portion not trained against racism and sexism, because social bias frame corpus that we use for that purpose is not really amenable for binary comparison mode. And people immediately started comparing like a black person versus white person, which is more morally acceptable. So we had to take it down immediately. Just over one weekend, there were 25,000 adversarial examples that people entered to our system. And I could never pay anyone to crowdsource such high-quality adversarial examples over one weekend. And I realized a lot of them were actually professors all over the world. And I thought, well, maybe professors don't have anything to do over the weekend. So probably things will calm down when Monday comes. And it turns out that's when everyone else does Twitter, so it became even more explosive. And then now we have about actually 4 million examples that the system received. So doing more Twitter was always my New Year's goals that I never seem to be able to abide by because my heart is not there. But I figured, okay, I might post one. Doing more tweet like other cool academics do, or spending all my weekend on Twitter, Delphi says it's wrong. And some people posted something fun like this. Should I make up a contrived adversarial example to torment a language model? And Delphi says it's a petty, don't do that. Yeah, after lots of fuss, New York Times reported about it as well. So there are some concerned voices I am willing to share. Actually, these guys changed the title of their write-up considerably. They really turned down afterwards. But basically, some people think that we should never, ever work on this, ever, because whatever we do, it's all wrong. So I think one of the concerns is that by doing so, AI might become moral authority over other people. And so it's a good concern to have. I don't think when we interact with each other following some moral understanding, we try to become the authority over each other. But AI, in order to interact with us safely, I think it should have some understanding. It cannot not have any understanding. So, and also, I don't endorse Delphi as authoritative use cases, such as being used as, AI judge in the courtroom. That sounds like such a bad idea. And then other concerns have to do with the fact that, well, moral models are too challenging. So whatever we do, probably it's unsafe at any accuracy, so just never work on it ever again. By that logic, by the way, I think we shouldn't work on fake news detection either, because I don't think we can ever detect fake news at 100% accuracy either. Whatever we do, I mean, depending on different political agenda, some people may think that it's a fake news and it's not. And I mean, there are many other things we cannot work because we will never obtain 100% accuracy. So I don't think the approach here is about 100% or not. The approach is more about understanding where the uncertainties and ambiguities and disagreement naturally arise. Because the way that humans interact with each other has a lot to do with whether I understand that this is a situation where I know that you're going to potentially disagree with me, and that's okay. So I think we just need to approach this differently. And in any case, we cannot stop the deployment of neural language models completely, and it's already making decisions that are riddled with moral implications. And some people seem to be more happy not to take any action, but I think taking an action is more important. It's a personal choice. Delphi will empower powerful people, marginalize other people, and I think it depends on how we approach this. We do need to invest a lot more research to represent diverse people, and in order to do so, we just need to do more such work, is how we view about it. So Delphi does have a bias. I will acknowledge that. It actually is a little bit left-leaning, which means from extreme left people, it's too right, and then from right people's perspective, it's too left. So, it's gonna get complaints all around regardless, but it's somewhat left-leaning in our analysis. And I think that's because there's a bit of a self-selection bias among crowd workers. There are crowd workers who like to work for us, and they tend to be a little bit left-leaning in our experience. I want to share how I ended up working on this. So we did this Alexa Prize challenge a while ago, 2017, and you need to deploy the system online. In order to not to make mistakes, we had a keyword list of things that never say. So just avoid the mentioning of all this, people's identity, which is completely wrong way to approach. It's as if they don't even exist, and that's really a strong form of discrimination against their existence. I was not happy about this approach. I think this is wrong approach. But in order to really lift this kind of problematic ways of avoiding sensitive keywords, we really need to invest more into this kind of research. And in order to do so, we really need to get at the core of the challenge. Sadly, this was the status quo in 2017. It's still the case right now. So in terms of fairness and justice, for anything that's obviously a good thing to abide by, like UN's Universal Declaration of Human Rights, Delphi is already pretty good at that, although it's not 100%. And because it's trained based on social bias frames, when you ask more in the free-form style question, it's able to do much better than what would have been possible using pre-trained neural models. So what kind of good use cases can we have? So I'm excited about this new work. Hyunwoo Kim is a student at Seoul National University who was interning at AI2. And together, we built this canary model that's based on pre-trained Delphi, just off-the-shelf Delphi, without requiring any further fine-tuning. And it's able to improve dialogue such that dialogue bot can have a position. Currently, the bots are overly agreeable with you to the point that whatever you say, morally questionable, is going to endorse whatever you say. That's not the correct way of building conversation model. So we should really have a conversation model that knows what's right and wrong and do not endorse something bad. And so we were able to improve even over GPT-3 instruct by using this Delphi-driven model, Canary. Another work that we did based on Delphi already appeared at Knuckle this year is in this text game setup called Jiminy Cricket, which is modal text games developed by people at Berkeley. We demonstrated that RL agent can learn much faster when powered with Delphi as prior knowledge to guide their learning. So you don't have to learn from scratch every single time you start learning. You can power that through some kind of foundation model. So there's a lot more work to be done, though, because it's a hard task. Okay, so let me share a bit of concluding remarks. The premise of this talk was that scaling laws are real. It's just unavoidable. Denial is futile. In fact, when the second paper of the scaling law paper series came out was the moment I realized that I need to really embrace this. No matter what I complain about, it's not going to work. And the powerful models based on large-scale neural networks are just amazing. On the other hand, common sense, knowledge, and reasoning, this is a moonshot research goal, and we cannot reach to the moon by building the tallest building in the world 1 inch taller at a time. You really have to have a different game plan. And I believe that scaling laws, or size of the model in general, is a necessary condition, so we have to have it, but not a sufficient condition. But it's a necessary condition, so we have to have it, but we need a different game plan. So with respect to the questions like this, no, we need something else than just a scale. And why this happens is because we are not really addressing the concept learning, proper concept learning. So in this talk, in terms of what we can do, I talked about different things, but let me just share a little bit more thoughts on the current paradigm of deep learning with respect to why the brittle behavior might happen. So this is what everyone typically does. Supervision on a lot of exam problems where correct answers are provided to you, combined with the self-supervision where you predict what's missing. This is not how humans learn. This is not how you win leaderboards if your leaderboards require you to generate answers, by the way. This happens only in the exam setup. And if you think about taking a deep learning class in which professor has 0 textbook, 0 lecture, I just give you lots of exam problems with the correct answer, and then lots of Python code. You cannot really learn efficiently, and this is what we're asking deep learning to do right now. We really learn from tutorials, textbooks, and from declarative knowledge, where the learning material is really written to guide you into the concept learning. And so drawing from that, I do believe in building knowledge models and then really declarative knowledge as a form of teaching AI models. And the common sense known bank that you saw earlier is some sort of a textbook to guide the neural network step by step toward what is right from wrong. All right, so that's all, and I'm now ready to take any questions. Yep.
A very good talk. Thank you. So I was wondering now, there are a lot of engineers working on end-to-end systems. And from your talk and many examples you have cited, it looks like you have to do some filtering of data so that you can build better models. So I was wondering if you can comment on data-driven and knowledge-driven, and then do we have to do some smart choice between data and knowledge in order to build a better model in the future?
Yeah, so the question is, end-to-end model seems to be the way to go in many recent literatures. And so this data engineering and decoding algorithms on top doesn't seem to fit into that framework. And so what's my comment on that? So for some time, I've been also writing end-to-end models, and I still do. Some papers are end-to-end models, and there's some benefit of end-to-end models, especially that we don't need to do feature engineering and just let the model figure out everything. But in doing so, we also neglect important research challenges such as, what about knowledge model? Can we have it as separate persistent model that can be used in many different applications? And I think we end up also not really making the best use of the power of, or the potential power of smaller models, and then keep increasing the size and compute of the model. So I do believe in diversity in the way that we approach research directions, and I do think it's really important to do things that appear to be somewhat out of fashion right now because the fashion keeps changing. There's one question here. I think that there's another question over there. Yeah.
Hi.
Yeah.
Thank you very much for your interesting talk. I was wondering about the concept of morality. You briefly touched on this at the end of your talk, but there's no universal morality. So what is your perspective on that?
Yeah, so I do think that this is what we presented is only a first shot approach. Ideally, we need to build much more diverse representation of moral perspectives, such that ideally the model should understand different moral frameworks, moral perspectives, cultural norms, and then be able to understand in what context people may have a different viewpoints. So I do believe in being able to actually build a model, not to do classification of yes and no, but being able to say, this is where people disagree as an actual output, and then being able to reason like how people tend to disagree, like in what way. That would be the most ideal way to approach.
Thank you.
Yeah.
Thank you for your talk. Very interesting. My question is that actually, when we teach AI, there are a kind of things that when we collect for the common sense as well as general talking, that we found out and astonished that there are lots of F talks or slangs and bad words and something like that, and people is angry at the attitude of AI. Actually, we are naturally doing something, but sometimes we have an attitude that our children. You're walking sidewalk, but you have to work right way or something like that. It's kind of paradoxical or something like it's a right path to do. What is your opinion? It's a wrong thing we have to teach something. Is any comment or right direction, something?
I'm not sure if I could hear you completely. I don't know if I understood your question right, but were you asking, maybe the question was, actually, I'm not even sure what the question was. Could you repeat the question? I think that the problem was also that the microphone was sometimes not close enough.
Okay. Actually, when collecting data from normal talking, so and teaching and training AI for our normal conversation, that people found out that it's full of slang words and bad words or something like that. So, and the people stop it, and by the way of talking, okay. But young people talking so many slangs and bad words. So my question is that if we teach AI for the common words of people, and in that case, it's different from what we really talk and something.
Gotcha. So the question is, in real life situations, humans seem to speak bad words, slang words, more so than perhaps what this resource might represent through a little bit cleaner annotations. So the answer is that the social bias frame that we included, it's very bad data in that it actually does include a lot of really toxic language that people do speak in real life situations. So the model is trained against that as well. And in some sense, those are actually easier ones to detect. The harder ones are the nuanced ones. Thank you for your question. There's another question in the yeah, I don't know. Whoever gets the microphone first.
Thank you for the talk. My question was on one of your examples. I don't remember exactly which one. I think it was the penny one with the plug socket. I noticed there was sort of a disclaimer in the Delphi's judgment, just saying it might be harmful. I was wondering if you could comment on how that was generated, and more generally, how we can, if there's an important space for models to be able to say, like, it's not sure or it doesn't know in certain situations.
Yeah, so great question. You may have noticed that sometimes there's no disclaimer in the examples that I used, and then there sometimes are. It has to do with the model update we had to make, or the online demo update, because we realized when we first released the demo, we did have a disclaimer, but at the corner of the website, and people never minded that, and then only cropped the middle part, and sometimes it looks really bad when the model does make a mistake. So then we put disclaimer inside, and while doing so, we also automatically tried to detect potentially toxic language to warn people that the example might contain something toxic. And so when that happens, the box becomes red, which is why for the Alexa Penny example, it was suddenly a red box. That detection is not perfect because the penny example, the coin example is not necessarily toxic, but that's where the state-of-the-art currently is. We used some sort of like state-of-the-art system in order to detect it. A lot more work to be done, really.
Thank you.
Hi, thank you. That was great. A question about the scaling laws. I think that there's no doubt that these large language models scale very nicely. However, the scaling exponents are super small, so it takes a ton of data. I'm wondering if there's a way to compare them with the approaches you proposed today on similar terms. So for example, could you look at whether these algorithms and the type of data you're using to train these models result in faster scale, or can be shown at least empirically that the scale is faster?
Yeah, that's a really great question. We didn't do the experiments that way, but my speculation shares the same intuition as yours, which is that probably the reason why scaling law seems to plateau has a lot to do with the diminishing gain. And we might be able to speed things up better by using better data or better algorithms. And another hypothetical remark about that is that even if people use large amount of data, if hypothetically, if we use very, very similar data, I don't think we will see the same kind of a trend. I think the power comes from the diversity of the data or complexity of the data. And so if we can find a way to increase the complexity of the data or diversity of the data, then I think we can see much better learning, even using relatively small data. Oh, and this reminds me of there actually are some data sets, one actually from my own work, but also by other people, where the data set is actually smaller than other off-the-shelf data sets, and yet lead to better out-of-domain generalization if the data set reflects more complex patterns despite the relatively smaller size.
Yeah, that makes a ton of sense. Thank you.
Yeah.
Thank you for the excellent talk. So what you're essentially saying is that in tasks such as common sense reasoning and moral judgment, there's no substitute for human supervision. And we have this issue in all sorts of tasks, and we come up with all these methods such as pseudo-labeling, proxy tasks, self-supervision. Do you think those principles could be applied to the tasks that you described to get around the scaling issues with human supervision?
Yeah, so do I think that's an interesting question. Maybe it's possible to design a model that can, without supervision, somehow reason about what's right from wrong by making better use of side information of the data. Because, for example, Reddit, we know that it's more morally problematic compared to Wikipedia, which is usually clean. So that may be possible, would be interesting direction to pursue further. I don't know what's the plan for the QA versus rest time, by the way. We started a bit late, but if organizers want to. Thank you.